Good evening, friends. Myself, Professor Moorthy Govindraj at Mechanical Engineering Department, Velammal Institute of Technology, Chennai. Yesterday we have discussed about various applications of robots in Mars exploration, in Earth, biological inspiration, mobile robot, then next industrial robot like KUKA robot, and future robot which is going to come for our humankind. And we have discussed about a lot of data related to robotics, how India is at present in the world market, what is the opportunity, and what are the applications robots can be used, how an engineers from various departments can contribute to design the robot. So we got a lot of insight about the robot. Now we all have some interest in designing a robot. So that is our everyone's aim. With this importance, today we are going to start our session 2 on industrial robotics and its application. The session 2 is all about robot kinematics. So you can able to see the picture here. This is the industrial robot. Actually, this is a small robot which is used in academic for learning purpose. But this robot is most widely used in industrial applications. We are going to study the robot kinematics of these types of robots as an initial stage. So we will move on to the next slide. So our outline of our presentation of robot kinematics comprises introduction, robot as mechanism, matrix representation of position and orientation. Later we will be going to discuss about homogeneous transformation matrices and how to represent the transformation matrix. Later about inverse transformation matrices. Then finally get into our interested topics, forward and reverse kinematics of robotics. Later, one of the very important representation, which is DH representation of forward kinematics of robot, which we are going to discuss in this session. So this is our outline of our presentation. Can you able to see the two pictures? These two pictures, you can able to see the coordinates. See, there is a coordinates. You can also see the coordinates here, 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 here. These are all the frames. These are all very important. We should learn, if we want to design this type of robots, we should be able to learn how to represent these coordinates of any robot which we are going to design to our need. So you can also see that there is how the robo is getting to revolve, that is revolute joint. You can also see the revolute joint here, 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 here. So this is very important. If we want to design a robo, this representation we should learn first, so that we can able to design the robot to our need. So with this as the importance, we will move on to the next slide. So coming to our first one, introduction, we should know what is forward kinematics and what is inverse kinematics. We should know what is forward kinematics and we should know what is inverse kinematics. See, before getting into forward kinematics and inverse kinematics, we should know the term what is kinematics, what is about. Hope everyone knows about kinematics. I will tell you a small thing about kinematics. Kinematics comes under kinetics. Kinetics can be split into two things. One is called kinematics and another one is called dynamics. In kinematics, what are the outputs we can expect? We can expect displacement, we can expect velocity, we can expect acceleration, that is linear displacement, linear displacement in the sense moving like this, linear displacement, linear velocity with respect to time. When you differentiate the displacement with respect to time, we used to get velocity, and once again when you differentiate velocity, we used to get acceleration. So this kinematics deals about displacement, velocity and acceleration of linear movement, and as well as it also deals with rotational displacement, rotational velocity omega and rotational angular velocity. This is all about kinematics. In kinematics, here no force is getting involved. So that is the reason robot kinematics, the heading is described as position analysis. We are going to find out not even velocity and acceleration here. We are going to find only the position of a particular robo, what position the robo has to reach at a particular point in space. So this is called what? Position analysis. So now you got what is kinematics. So kinematics deals about displacement, velocity and acceleration, linear as well as rotational. It doesn't take any force into account. Whereas in dynamics, it includes all kinematics parameters, plus it includes force also. In dynamics, Newton's law, it will be considered, whereas in kinematics it is not considered. Okay. Now coming to forward. Now we'll come to forward kinematics. So what is forward kinematics? Any robo will have links and joints. We will discuss what is links and what is joints in coming slides. Just keep in mind, robo will have links. For example, if I take myself as a robo, see the body, I'm moving this side, I'm moving this side. So this is one joint, hip, and this is called upper arm. This is called upper arm, and this is called lower arm. This is my wrist. So we are going to design only this thing, this robo as an industrial. We are going to consider only this thing as an industrial robo. So how many degrees of freedom? Now I have, for example, I'm sitting on the chair. How many degrees of freedom I have? I'm just moving. See, 1 degree of freedom in the hip. Then this one, it is moving 2 degree of freedom. This one, another degree of freedom. So how many? And this is the another one. So 4 degrees of freedom. When you increase the degrees of freedom, the complexity of the mathematical thing will get increases. So what we used to do, we used to go with a simple degrees of freedom like 2 degrees of freedom or 3 degrees of freedom robot design. Next. Okay, we are talking about degrees of freedom, is it? What is it? What is the degrees of freedom? Degrees of freedom, I will tell you. You take any object. You take any object. I am taking an object called pen. This is my object. This object in space, it will have how many degrees of freedom? It has 6 degrees of freedom. How? For example, this is the object. See, I am placing this is the object. This object can move in x direction, y direction, then z direction. Clear? The object can move in x direction, y direction, and z direction. So only we have 3 directions. So we have 3 degrees of freedom in linear movement, and as well as this object can revolve about x-axis. Can you able to see it? It can revolve about x-axis. We consider this axis as y-axis. So it can revolve about y-axis, and it can revolve about z-axis. Can you able to see? You can revolve about z-axis. So how many degrees of freedom of any object in space it has? It has 6 degrees of freedom, 3 translational and 3 rotational degrees of freedom. So any object in space will have 6 degrees of freedom. We should understand this concept to design the robot. Everyone should have this understanding. This is very important. Okay? Now you know what is degrees of freedom. Next. So now come to the forward kinematics. Forward kinematics to determine where the robot hand is. If all joints variables are known. What is the joint variables? The joint has, what is the joint? If it is a rotational joint, it has theta. If it is a translational joint, it has what? It has what? Linear movement, displacement. So rotational displacement theta and d. So if we know theta and d, we can able to find the robot end effector. Yesterday we have discussed about end effector. End effector is what? West. This is the end effector. See how this human end effector is one of the best end effector in the world. End effector. We can hold any object of any different shapes and with more grip. This is the design. This is the best, one of the best design of end effector. Okay. So what is forward kinematics? To determine where the robot hand is, that is the wrist is. What we know, if all joint variables are known. What are the joint variables? It may be theta or displacement. Okay. Now you got what is forward kinematics. Okay. Knowing displacement and as well as velocity, you can able to find the end effector position in the space. That is called forward kinematics. Clear? Okay. Coming to the next, inverse kinematics. Inverse kinematics, what is that? To calculate what each joint variable is. What does it mean? Suppose we know the end effector position. We know what? The end effector position of a robot in space. For example, in space, what is the position we know? We know x, y, z position. In space, how many coordinates we have? We have 3 coordinates. One is called x coordinate, the other is called y coordinate, and the other one is called z coordinate. So in space, we have how many coordinates? 3 coordinates. So in space, we know 3 points. Knowing the 3 points, we should be able to design, we should be able to come up with the theta and as well as displacement. The variable which is called theta and displacement, that is called inverse kinematics. Okay, you got very clearly what is forward kinematics. Forward kinematics, we will be knowing theta and displacement, translation joint displacement. We will be finding out the point in the space of the end effector. Whereas in inverse kinematics, we will be knowing the end effector point in space, that is xyz point in space. Knowing that point, we will be finding out theta and as well as what? D displacement for the translational. So link displacement. Okay. So this is called inverse kinematics. Can we move on to the next slide? Okay. Next topic is robot as mechanism. Yes. Any robot is a mechanism. What is mechanism? Mechanism will have links and joints. Mechanism will have links and joints. Now I will tell you what is links, what is joints here. Okay, we will discuss all the joints here. So what is mechanism? Mechanism is consist of link. This is called link. O1 A is one of the link, and another link AB is another link. BO2 is the other link. O2 O1 is the other link. But we are not drawing this. Okay, it is fixed. So this link, if we want to connect 2 links, see, this link will have a 6 degrees of freedom. This link in space, it will have 6 degrees of freedom. This link will have how many degrees of freedom? 6 degrees of freedom. This link, it will have 6 degrees of freedom. Okay. So what I am going to do, I am going to connect this link. Suppose you forget about the link AB, BO2. You just consider only the link which is O1A. So if you consider only the link will have 6 degrees of freedom. What I am going to do, I am going to constrain it in a planar. What do you mean by planar? Planar is something like in a plane. What is planar? In a plane surface. You are writing on a scribbling pad, you are writing on the note. The paper, we call it as a planar. What is it? The bigger one, it's called as y-axis, and the smaller one, we call it as a x-axis. So like this, here this is a planar. So this is a planar mechanism. So planar mechanism, here at O1, it is constrained with pin joint. O1, it is constrained with pin joint. So what happened? In planar mechanism, it has only 3 degrees of freedom. In planar mechanism, it has only 3 degrees of freedom. For example, you consider the screen. You consider the screen. The screen, it has x direction, and this is y direction. Okay, you got it? So you have 2 degrees of freedom here, and one more direction which is perpendicular to the screen, which is z-axis. In z-axis, what you can do is you can rotate. So in a planar, if the link is in one planar, one particular plane, it has only 3 degrees of freedom. What is the degrees of freedom here? X. Displacement about x-axis, displacement about y-axis, and rotational about z-axis. Now you know in planar mechanism you have 3 degrees of freedom. So what I am going to do, I am going to put one revolute joint. If I put one revolute joint, what will happen? One end of the link is get into fixed with this pin joint. What will happen? This link can be able to move in x direction. We cannot able to move. Can be able to move in this direction, y direction. We cannot able to move because it is fixed. The pin is fixed here. So what degrees of freedom it has? Only it can rotate. Only it can rotate about clock, that is anti-clockwise and clockwise direction. Only it can rotate about anti-clockwise and as well as clockwise direction. So how many degrees of freedom? Now it has only 1 degrees of freedom. How many degrees of freedom? Only 1 degrees of freedom. Before the link in space, how many degrees of freedom it has? It has 6 degrees of freedom. This link has in space 6 degrees of freedom. In planar, it has only 3 degrees of freedom. Since it is constrained with a joint called pin joint is called revolute joint, the displacement in x and y got constrained. Only it can move, that is rotate about z-axis. That is z-axis. Where is the z-axis? The z-axis is inside the screen, that is the perpendicular to the screen inside, perpendicular to the screen which is inside. How can you represent? Can you able to represent perpendicular in 2D? It is very difficult. What is the way you can write? You can draw like this. That is inside the screen. Outside, this is this side outside. So this we can draw like this. So it is revolved about z-axis. Now you got what is the degrees of freedom it has? It has only single degree freedom. Okay. Then next, you are going to connect that one more link, which is the link called AB. In space, this link will have how many degrees of freedom? It has 6 degrees of freedom. You are constraining here. You are constrained. And other end also it is constrained. Clear? Similarly, you have one more link here. See here. This is also constrained with O2 and B. So the link, what will happen? So how much degrees of freedom this has? Only single degrees of freedom. All other degrees of freedom, it is constrained. So this mechanism is having only how many degrees of freedom? 1 degrees of freedom. That is the reason we given as here 1 degrees of freedom closed loop 4-bar mechanism. Why we call it as a 4-bar mechanism? See, this is 1 bar, this is the another bar, and this is the another bar, and one more bar is there. If there is a bar which is O2 and O1, we can draw, or we don't want to draw. It's our freedom whether we can draw it or not. So this 4-bar mechanism will have single degree of freedom. What does it mean? What does it mean? It means that if I have a motor, if the motor is fixed, if I put a motor, the motor will have a shaft, is it? Motor will have a shaft. If I fix the motor to this link, what will happen? This link will get to rotate. How much degree? It can rotate to 360 degree. It can rotate to 360 degree, this side or that side. So once it is rotating, the link accordingly AB and BO will rock. This will get to rock this side and that side. This will rotate because the link is very small. It can rotate 360 degree. So you can put only one motor. That is the reason we call it as a 1 degrees of freedom closed loop 4-bar mechanism. Clear? Now we will move on to the next closed loop and open loop mechanism. See, what we discussed is a 4-bar mechanism, which is a closed loop mechanisms. So here you can see the same thing. Here in this closed loop, there is a 4 link O1A, A2B, B2, O2, and there is a one more link which we already discussed, O2, O1. So this link is a fixed link. It doesn't matter whether we draw it or not, there is a link, okay. So this 4-bar mechanism has 1 degrees of freedom, which we have discussed. If we give an input to this at the point O1, if we fix a motor, this will turn to rotate 360 degree in clockwise or anti-clockwise. Accordingly, since it is connected, since the O1A is connected to AB link and BO2 link, this link AB is a coupler link, we call as a coupler link, which couples this 2 link O2 and B and O1 and A. See, we call this link as a coupler link, and this link BO2 is a rocker. You will have a rocking mechanism, something like it will slide only up to here and here. But this link, the small link, it will revolve full 360 degree, clockwise or anti-clockwise, according to our input. So only one input is required to move this link, to move this mechanisms. So we call it as a single degree of freedom. Okay, coming to the next open loop mechanism. In open loop mechanism, we can able to see that the links, it is not closed, it is open. That is the reason it is called open loop mechanism. This we call it as a robot manipulator. Okay, this we call it as a robot manipulator. You can see that here O1 A is one link, A from A to B is the other link, and B to C is the other link. Something like this is something like our body, and this is the upper arm, and this is the lower arm, and here you will have an end effector, that is our hand. From here you will have an end effector. So it is like a humanoid robo, or we call it as a robo manipulator. So manipulators are, industrial manipulators are open loop mechanism. Most of the industrial manipulators are open loop mechanisms. So we are going to discuss about this open loop mechanism in coming slides, and the interest is we are going to design only this open loop mechanism. We are going to design only this open loop mechanism. This is our interest. Okay, next. And in this open loop, you can fix this, that you can have one joint here, you can have one joint here, you can have one joint here. So totally how many joints you can have? 1, 2, 3, 4, and there is, if you fix one end effector, I told that end effector will not come when you buy the robots from the industries. End effector is an extra attachment. So this end effector will have its own degrees of freedom. Currently this manipulator have 4 degrees of freedom. Okay. Coming to the next slide. So we have discussed. So we have discussed before degrees of freedom. We have discussed degrees of freedom, and we have discussed the mechanisms, and we have discussed about robot manipulators. So to have a better understanding, we will show you. We will see some video clips so that we will have a better understanding of degrees of freedom and what is 4-bar mechanism, how the mechanism it performs, and how the robot open loop mechanism performs. So that will give much idea and knowledge for us to get into a robot design in coming days. Okay. So robot acts as a mechanism. Okay, in mechanism, degrees of freedom is a very important thing. Okay, what we are going to discuss, what we are going to see in the video clips, understanding the degrees of freedom in robot kinematics. That is, in robot, how degrees of freedom we need to understand. This clip will give you the idea about that. And we have one more clips, understanding the degree of freedom in civil structure. You had seen a lot of civil structures in your daily life. You had seen a lot of bridges, you had seen a lot of cantilever beams and structures, your house structures. So you can see the understanding of degrees of freedom in civil structure by these clips, the small clips. Okay, next is, we have discussed previously the 4-bar mechanism. We have told that the small link will rotate, and there is a coupler link which is AB, and there is a rocker link which is B2 O2. So we will see that how the 4-bar mechanism is going to works from this clippings. And finally, we will go to the open loop manipulators, which is the robo. That is the industrial robo. This is the interest. This is the area of interest which we need to develop. Okay, students can develop. This will give you a better idea, better understanding how industrial robots are there. You can able to see a small clip here. It is a high accuracy small 6-axis industrial robot, a very small robot and very high accuracy robot. By seeing the clip, we will get a lot of ideas and what is the degrees of freedom that industrial robo has. We can able to see it in the video clips, and we can also see one more video clips which represents 6-axis industrial robots, so that we will get ideas how to by seeing the robot how we can tell the degrees of freedoms. So that is the reason we are going to have these clips. That is the idea. Okay, and this first two small video clips is from the industry side. And the next two clips is from the academic side. You will be coming to know how the students had come out with industrial robot in the universities with with a small team from each department. See, as we discussed before, robot can be designed with a combination of knowledge from all the department. So if you have some friends in some other departments like computer science, IT, electronics and electrical, what you can do is you just mingle together and form a team, start doing start designing a robot. It is very easy. If you start today, by the end of 6 months or 1 year, you will get a robot. Once you develop a robot, you can market those robots in India and as well as abroad. So later stage, you can design the robot. Initially, you will be designing for a small simple robot. Once you got a lot of ideas, you can explore to design robot according to the requirement of the needs from the industries, from various companies in India and as well as abroad. So this is all about what we are going to discuss is all about industrial robot. Okay, industrial robot, it finds a lot of applications in industry, particularly in assembly, pick and place robot for welding purpose, for painting purpose. If there is going to be hazardous place, something like high temperature, we can use this robot. To place a material in a conveyor belt, you can use this robot. Okay, for repetitive work, you can use this robot. This robot is called a Puma robot. Okay, industrial robot. It has a wide range of applications. One of the things is we need to design it. For designing, we need this robot kinematics that we are going to discuss. Okay, and students also come out with 3 and 4 degrees of freedom industrial robot, which is a very simple robot. You can get admired with these clips, so that in coming days you can also design the small industrial robot in your college with your support of your professors, and with all the department put together you can design a robot. Okay, we'll go on. We'll see the clip of degrees of freedom.
What is 6 degrees of freedom, or 6DOF for short? 6DOF refers to the freedom of movement of a rigid body in 3-dimensional space. But anyone can Google 6DOF and get that definition. What does it actually mean? Put simply, the degrees of freedom refer to the ways our bodies and other objects can move through the space around us. Take the space shuttle, for example. It can move along 3 axes that are commonly referred to as the Cartesian, or X, Y, and Z plane, which you might remember from algebra class. It can move forward or backward on the X-axis, left and right on the Y-axis, and up and down on the Z-axis. There are, however, 3 more movements the shuttle can make. The shuttle can roll on the X-axis, it can pitch forward or backward on the Y-axis, and it can rotate or yaw in a circle on the Z-axis. Those are the 6 basic movements, or degrees of freedom, that any object can make. But not every object can move in all 6 degrees. Fingers, for example, can't move independently of the hand in the X, Y, and Z planes, but they do have pitch, roll, and yaw capabilities. So if there are only 6 degrees of freedom, how can we see robots that have 20 or more degrees of freedom? Each moving part or joint on the robot has up to 6 DOF. Returning to fingers, each one has 3 degrees of freedom, as do wrists, elbows, and shoulders. Our hips, knees, ankles, toes, necks, even ears have their own degrees of freedom, and they all add up. And in manufacturing, each joint and the 6 potential degrees of freedom that come with it represents a value that must be captured and tracked to ensure accuracy. This makes having a laser tracker that can capture all 6 DOF for the probe or sensor measuring a part essential in today's automated manufacturing environments. To learn more about 6 DOF and its applications in automation, please visit apimetrology.com and contact us to speak to a metrology expert.
Okay. Now you got a clear understanding of degrees of freedom. What is degrees of freedom? Particularly in robots. Okay? Okay. Good. Now you can have a understanding of degrees of freedom in civil structure. We should know degrees of freedom to design
Explain the concept of degree of freedom. In the displacement method of analysis, joint displacements are the primary unknowns. These joint displacements are commonly referred to as the degrees of freedom of the structure. It is necessary to consider all the independent degrees of freedom while writing the equilibrium equations. These degrees of freedom are specified at supports, joints, and at the free ends. Let's consider a prop cantilever beam to understand degrees of freedom. The beam under action of load P will undergo only rotation at B if axial deformation is neglected. Thus, the kinematic degree of freedom of the propped cantilever beam is only 1. And it is denoted by theta B, which can be calculated by finding slope at B. Thus, for the continuous beam having node A, B, C, and D, there are 5 number of degrees of freedom. Thus, we can summarize as.
Okay. Hope now you got what is degrees of freedom in civil structures. This is very important. Okay, all structures, all objects in space have 6 degrees of freedom. We need to constrain it so that if a particular degrees of freedom is constrained, we will leave some particular degrees of freedom so that that particular degrees of freedom we will make use of it. Okay, in mechanism. Okay. Now coming to 4-bar mechanism. We told that 1 degrees of freedom. It is a 1 degrees of freedom, and we have told that the smaller link will revolve, and there is a coupler A, B, and one more. The rocker is there from B to O2. The rocker will swing like to and fro. Okay, you just see the mechanism, so you will get an understanding how the 4-bar mechanism it works. See how we told you, we have discussed the small link will revolve, so which is connected to the link A and B and O2. We told that this link is a coupler link and this link is a rocker link. It rocks from here to here, here to here. Okay, the smaller one will revolve, which is fixed to the motor. Okay, got now you got an understanding of 4-bar mechanism, which is a single degree of freedom. Only one motor you can fit. If you put one more motor, this become redundant. This will not work. Okay, this will not work. That is called redundant. So 1 degree freedom mechanism, 4-bar mechanism. Okay, next coming to open loop manipulators. Open loop manipulators are industrial robots. So we will see the first video clips. High accuracy, small 6-axis industrial robot from the industries. One, two, okay, now you got the understanding of 6-axis small industrial robot. This robot is having a 6 degrees of freedom. Okay, this robot, it needs all department students' knowledge to design it. There is a control, you need to program, you need a link, you need to manufacture. So there is an electrical motor. So electrical department has to be come inside. So all department, it needs to build this small industrial robot. Okay. Next, we will move on to the next video clips. Now you can able to learn what are the degrees of freedom in a particular robot. This video will give you better understanding and insight how you can tell particular robots having particular degrees of freedom. Okay, you just see the clip now. Video clips. It's a very small clip. This is from Fanuc. 6-axis robot. Now you can see. Got it? Second one. Third one. Fourth one. Fifth one. Sixth one. That is end effector. This is the end effector. This end effector, it's having only 1 degree of freedom. Each axis is controlled by servo motor. The robot is programmed with the teach pendant, computer science department, to write the program. According to the program, the robot will move. Puma robot. Application of all application in gripper. These are all grippers. According to the application, the gripper will change. Magnetic gripper, suction gripper. This is how a standard 6-axis robot works. Wow, good. Now you got a clear idea how to define degrees of freedom in the industrial robot. Okay? Hope this video will help you to have a good understanding of degrees of freedom in industrial robot. Now coming to the students' contributions in universities. See the Indian student.
16th grade robot kinematics and dynamics. The goal to learn more about all the mathematics behind robots, about all the practical considerations like tuning and so on. Just generally be able to use robots. So we were given these robots and a little bit of starter code like making for controlling the motor. And then we're given the position of the mouth, and then we have to find a trajectory of different waypoints and so on. We scoop up the pellets and drop them out without spilling it. This little impossible. Basically just simulating as if this is a person who can't use their arms anymore, who now needs a robot to help assist them. Inverse kinematics, forward kinematics, is basically trying to get robots to do what they're supposed to do. Given the position that you want the robot to be, so you want the spoon to be inside of the bowl, figure out what position you need to send each of the joints to get the robot to actually go to that position. Yeah, basically because you're going backwards. With the other direction, forward kinematics is if you know what position all the motors are in, then where will the robot end up? This is the opposite. Anyone ready to do another one? sometimes it actually hit the face. Usually I don't put the spoon on when I'm testing. I'm not sure where it's going to go. Because otherwise those spoons get just big. There's that reflex. What time is that?
Okay, so you had seen that students has constructed a small robo which is of 5 degrees of freedom. They are doing a lot of programs to make that. See that the robo is taking some feeding material and it is feeding to some mouth of the figure of a person. You had seen it. What they are doing is they are changing the place of the feeding bowl somewhere. So they are trying to change the program, and even by using sensors they want to automate. That is what they are trying. If you do this type of robot in your colleges with a team of students with the support of professors, it will be very good and it will be very interesting. So we can able to contribute to our Indian industry market and as well as abroad also. Because Industry 4.0 it needs a lot of industrial robot in coming days. So this will have a good interest. This will make you a good interest in building that is design and developing robot in your college with a team of bunch of young students. Now you can see that some students are designing a small robot which is 3 and 4 degrees of robot for certain applications like pick and place. They are using 2 types of robots. So accordingly they are doing some automations. You can see this. They want to do some automation in the industry. See this logo? 1, 2, 3. 1, 2, 3. Okay, you got it. So what they have done is they have done some automation process for a particular industries. They have used 2 robots. One is 3 degrees of freedom and another one is 4 degrees of freedom robot. This is the 4 degrees of freedom robot. Here one more degrees of freedom is they had included so that it will take the material from here and it will place it in the bin so that it will travel. So this robot is having one more degrees of freedom when compared to the previous robot which has only 3 degrees of freedom. Okay. So this is all about the students project. If you get involved, you can also able to do. Only thing is some mathematics we need to learn, concepts of kinematics and control system. It is there. So you got an idea to design 3 and 4 degrees of freedom students industrial robot. So with this we had covered robot as mechanism. Yes, robot is a mechanism. So now you know what is degrees of freedom, what is 1 degrees of freedom in a closed loop mechanism. Now you know what is manipulators on industrial robots, open loop industrial robots. Okay, and we have seen industrial robots of smaller size and the bigger one, industrial robot, and we have also seen that student made industrial robots for particular applications. So with this we had covered introductions, mechanism as robot. The rest of the things are all mathematics, matrix representation from here to here, homogeneous transformation matrix. It needs only a simple mathematics. If you are good at matrices in your 12th standard, that is sufficient to learn homogeneous transformation matrix for transferring from one position to another position, and then representation of transformations, and then this inverse transformation matrix is a very important thing. Knowing the position in the space, we need to find the variables like theta and d displacement. That is the inverse transformation matrix, which is very important. This is very important to design the robot. Then coming to forward and reverse kinematics of robotics. This is our topic of interest, which we are going to cover in coming days. And DH representation of parameters, that is Dynamic-Hartenberg parameters of a forward kinematics of robots. So this is one of the simplest representation of forward kinematics, doing forward kinematics. If you know theta and displacement of a particular one frame to another frame, if you have even n number of frames, n number of degrees of freedom, this DS representation will take you to design that particular robot very easily. Why? Because if you go with the basics homogeneous transformation, it is a very tedious process. So to simplify that, this is a very important thing, that is DH, Dynamic-Hartenberg representation method. It's very useful for forward kinematics of robotics. So what we can do is, hope we have covered the introduction and robot as mechanism. We will, because almost 1 hour it is covered to learn this basics. The rest of the things is easy. So what we can do is, we can the next section we will learn matrix representation, homogeneous transformation matrix, representation of transformation, and inverse kinematic transformation. And this we will have one session for this 4, and we will have one more session for this 2, so that we will get a better understanding to design the robot, at least a simple robot in your college. Okay, so with this I will close this session. We will have 2 more sessions as a continuation of industrial robotics and its application in coming days. So what we can do is, later we have all your database, your contact number and your mail ID. What we do is, once we get ready, we will post it in the YouTube. You can just go through it, so that in coming days you can design a small industrial robot for your application or industrial application. Thank you. With this I close my session. Now I am very thankful. Now any queries, you can just if you have any queries, you can you just text it here. My number, it's a WhatsApp number 9080567373, and you can also send a mail, Moorthy dr.g1979@gmail.com. So we will answer to your queries immediately. Thank you to one and all. Thank you for watching. Okay. Now I'm very thankful to the management of Mahindra Institute of Technology for giving this opportunity to present to many institutions, and I am very thankful to Professor Ganesan and Principal of Mahindra Institute of Technology and the Management, and I am also very thankful to our management, Velammal Institute of Technology, Chennai, for given opportunity to represent ourselves to the students of engineering colleges in Tamil Nadu. Thank you one and all. Thank you so much. Thank you for watching. Thank you.